Hello everyone, today we're going to continue on 3.2 and I think today will be the last video for 3.2. So if you recall, the last thing we talked about was to talk about different kind of subspaces. One of the most important subspaces that we're going to talk about will be the continuous derivative function space, which is a subspace which are subspace of a continuous function space. The reason why these are very important because we are going to try to form the solution set of a differential equation, and since solution set of a differential equation are usually functions, so therefore we can now use the function space to describe the solution. And in order for that to work, because differential equation also involve derivatives, so we need to know the function space have what we call derivative function space that kind of give us the derivative of the function. So you'll see how all that play out when we get to chapter 10, when we first talk about forming solution of a differential equation. So today the last thing I want to talk to you about is the following. So as I say, we try to use vector space and subspace to kind of describe the solution to a differential equation. And because of that, we want to have some simple way to describe vector spaces. And so far, all we can do is to just simply identify them using some board criteria like, continuous functions or polynomials. But now what we want to do is want to try to create some smaller vector spaces, or actually technically speaking, smaller subspaces that are more specific to what we need. So to do that, we're going to learn about this concept called span. Definition. Given a set of vectors, let's say S, in a vector space V. So So set of vector in here, this set of vector is kind of like a subset of element in vector space V. So in a sense, it's kind of like we're forming subspaces. Okay, but of course this is slightly different. So let's say this set of vector S consists of, let's say, vector S1, vector S2, to vector sk. So now I'm going to define this term, the span of S, which use this square bracket symbol. The span of S is the set of all possible linear combination of S. So therefore, meaning that if I take the span of S, that basically means, I'm taking the set of all linear combination. So linear combination is formed by something like this, where the a sub I are the scalar So therefore, basically meaning that the span of S basically refer to anything in this form. For kind of all possible a sub I within R. So here meaning that a sub 1 can be any real numbers from negative infinity to positive infinity. A sub 2 can be any real number from negative infinity to positive infinity, and so on and so forth until a sub k. So that form what we call the span of S. Now, interesting thing to note is that if vector S1 to Sk represent vectors in Rn, then this expression right here will form some kind of k-plane within Rn. Okay, which is technically speaking a vector is a subspace. So that actually would be explained by this theorem. theorems 3.2.4, which states the following: let S be a subset of vector space W, and let's say V is the span of S. Then what we know is that V is a subspace, of W. Now that might seem a little hard to understand, but how about I show you an example, kind of illustrate what this concept is. So the idea here, so first of all, make sure you understand, is that the idea here is try to use the span to describe subspaces. That's what we try to do. So show you. So here's an example. Let's say we talk about vectors in Rn. So in this case, our Rn is our vector space. I'm going to define two vectors in Rn. Let's say vector u, which is 1, 0, ... 0, and just n minus 1, 0 with the 1 in front. And let's say vector v is 0, 1, 0, ... 2, 0 at the end. So let's consider S, the set of S, being the vector u1 and u2. So I'm going to define V to be equal to the span of S. So what does that mean? That basically simply means that all vector X in this form. Actually, since I'm not using subscript, maybe I just use this. And what does this look like? Well, that looked like a two planes in Rn. So that's basically how you form a subspace in Rn, is by taking some vectors and then form the span of that. Now, the nice thing about that is, now that I can look at this, I can now actually define element within the vector, this subspace, without relying on some, I guess, condition, which sometimes may be ambiguous, sometimes might be hard to define. Now, show you, maybe show you a very more specific example in Rn. How about this one? Imagine we have R3 as our vector space. Then I'm going to go and let vector u be the vector 1, 0, 0, and vector v become the vector 0, 1, 0. Then the span, then S would be, once again, the vector u, vector v. So what is the span of our set F? So the span, let's say V is the span of S, then therefore just become this vector X equal to A times 1, 0, 0 plus B, plus B times 0, 1, 0. So what does that actually come out to be? Well, actually that come out to be this. Would basically just become AB0. So that actually just formed the XY plane in R3. Because Z coordinate is 0, and then the X and the Y coordinate can be any numbers we want. Which, by the way, this XY plane is a two plane. And both of these two span would form a subspace within the vector space that they're in. Now, using a span, some of you actually might recall learning something last year in multivariable calculus. As a matter of fact, it's chapter 1 that you learned this. That this whole concept might kind of remind you of that. If you think about it, we are essentially using, in this case, in both of these examples, essentially using vector u1 and u2 as the building blocks that we use to build the vector x. And then in order to build vector x by using u and v, we need a specific number of u and a specific number of v to do that. So of course, the first thing that comes off the top of your head is that this would tell me that vector x is a linear combination of u and v. That's not true. I mean, that's not bad. That's definitely true. And that's definitely something you learn in chapter 1. As a matter of fact, right in the beginning. 1.1, that's when you learn it. But here, I'm also more referring to something else that you also learned in 1.1 last year. And that will be the concept of coordinates and bases. In this case, when I form this span of S, we are technically speaking using S as our basis. And then now the specific coordinates in front of the basis are now basically become what we call the coordinates. So therefore, in a sense, we try to describe a vector space using a span. We are basically more or less providing a basis for the vector space, in which we can use to kind of generate all the possible elements within the vector space or the subspace. Now, I'll give you another example to try to illustrate that concept. So as you probably remember learning from last year, when you're defining bases, they are actually, you could actually define a basis using many different bases, using many different vectors. So therefore, meaning the same vector space could have multiple bases, and that would change the way the coordinate work. So give you a very simple example. Imagine the following. Imagine the polynomial space, P sub n. Okay? I can define P sub 3, which would be a subspace of P sub n, to be this, to be the span, the span of the following vector. Now, before we actually move on, there's something very important we have to talk about. Number one, whenever you're defining a span of a set of vector, you must use those vectors that come from within the vector space. So in here, I cannot use like radical x, I cannot use x to the fourth or anything like that, because I have to use polynomials of third degree or less in order to do that. So the most basic one would be 1x, x squared, x to the third. For that would span the entire polynomial space of 3 degrees or less. Why? Because if I look at any element within P sub 3, they will look something like this. So in here, if I look at 1x, x squared, x to the third as my vectors, then I'm just simply forming a linear combination of those 4 things. And when I do that, they become a polynomial of degree 3 or less. As a matter of fact, interesting thing to note that you probably want to write down for yourself is that this span right here, 1x, x squared, x to the third, is probably considered to be the standard basis for polynomial space. Now, with that being said, that would imply there are non-standard bases, and there are. They would just, look different, but they can still span the entire space. So show you a second way to define P3 using a different span. I can easily do this span. So that would also work as a span. The reason why I would show you. So that would imply that any element must equal to something like this. So if I form the span, I will basically forming P of x equal to, let's say, I'm going to use a different letter. B sub 0 plus B sub 1 times x plus 1 plus B sub 2 times x squared plus x plus 1 plus B sub 3 times x to the third plus x squared plus x plus 1. Now, without doing anything, I can clearly see one thing is true. If I look at the first span right here, I can see that clearly I can only generate in this form, I can only generate something that's to the x to the third power. There's no way for no matter what I choose for x, a sub 0, a sub 1, a sub 2, a sub 3, because they're all new number or scalar, that can only give me a polynomial in x in third degrees. If I look at this expression right here, well, guess what? It's the same thing. This expression only allows me to form polynomial of third degrees. Now, however, just because of that doesn't mean that it can actually span the entire P3. That's the tricky part. Why is it a tricky part? Because it's possible that I could have a degree polynomial of third degrees, meaning I can form, using this span, to form a degree of x to the third power as the highest power, but it might not allow me to form a specific type of polynomial because some of the coefficient might force some of these elements to be missing. See, it's easy to see that this would always work because I can just pick any number for a sub 1, any number for a sub 2, any number for a sub 3, any number for a sub a sub 0, a sub 1, a sub 2, and a sub 3, and to fit in any polynomial, meaning I can arbitrarily find any polynomial. Let's say I've given this polynomial p of x equal to 1 minus 2x plus 3x squared plus 7x to the third. Then I can say, oh, that just basically means that I have x sub 0 equal to 1, x sub 2 equal to negative 2, and then a sub 1 equal to a sub 0 equal to 1, a sub 1 equal to negative 2, and a sub 2 equal to 3, and a sub 3 equal to 7. So that becomes the specific set of scalar along with this span that will allow me to form this particular specific polynomial function. And it shouldn't be too hard for you to just think about it and understand that no matter what polynomial function I write down in the 3 degrees or less, I can write pretty much anything here, you will always be able to find this set of numbers with this span that will represent it. Okay, it will be impossible for me to form a specific polynomial function that I won't be able to find these 4 numbers along with these four vectors to form that polynomial. Now, however, it might not be the case when you do a span like this right here. So there are certain conditions that's required in order for that to be true. So that condition is often referred to as linear independence. So that is something that I won't be able to talk to you about until later on, because a later section will talk more about it. But here I can pretty much assure you that this would always work also because of the way that I construct it. Okay? And you can actually try something like this. So I'm going to go ahead and ask you to see if you can try something like this. What if I take this polynomial function right here, and ask you to find out what is b sub 0, b sub 1, b sub 2, and b sub 3. Will you be able to figure out what that is? All right. So now, with that being said, you can actually kind of try to give that a try, and maybe during class we can go over it. Or maybe when we have time, I can give you a head start on this. I do want to finish up the last thing I want to show you. So one of the reasons why we're defining span is so that we can actually now form subspaces rather easily by say providing a span for it. So example, let's say we look at the continuous function space. Oops. So the first thing you need to notice is that the continuous function space is really broad because you can pretty much put any kind of functions as long as they're continuous. But also, even if you have functions that are not continuous from negative infinity to positive infinity, you can still define them to be in a continuous function space by restricting the domain from A to B. So now I can actually form subspaces. We can form subspaces within the continuous function space by providing a span. Just like this. The first one. Suppose I look at S to be the set of 1x squared. Then the span of S would basically be any function in the form of which basically form the subspace of all polynomial function of degree 2 or less. Or we call them the polynomial function space P sub 2. Good? And the interesting thing about it is, in this picture right here, I can, in here, notice that I'm forming this subspace by using A sub 0, A sub 1, A sub 2. Therefore, this particular subspace actually work out very similar to a R3 space, where instead of having like 1, 0, 0, 0, 1, 0, and 0, 0, 1 as my span, I now have 1x squared as my span. But that would form a three-dimensional space almost identical to a R3 space. But is that a surprise to you? Well, it shouldn't be, because we're established that P sub 2 or P sub n is the same as R to the n plus 1. Now I can also form this subspace by doing the following. By forming so if I form S to be the set of 1 cosine x sine x, then what would be the span of S going to be? Well, the span of S would be any continuous function in the form of A sub 0 plus A1 cosine x, plus A2 sine x. And I know for a fact that this will form a subspace because the following. Recall, in order for a vector, for a subset of object to form a subspace, it must satisfy three conditions. The first one, it must have the 0 element in it, and I can say that 0 element is in this span. The reason, because it will become 0 plus 0 cosine x plus 0 sine x, and that gives me 0. So therefore, the 0 function does take into this form with this very specific A sub 0, A sub 1, A sub 2 all being 0. Is that a surprise? No, because the 0 element in here is essentially the same thing as the 0 element in R3, which is the 0 vector. Okay, so you think about it, the function z of x is equal to 0, basically meaning that z of x is equal to 0 plus 0 cosine x plus 0 sine x. Essentially the same thing as the 0, 0 vector in R3. That's how the 0 element works. What happens if I want to add two functions together? What if I have f of x is equal to a sub 0 plus a sub 1 cosine x plus a sub 2 sine x, and I have a second function g of x, which is b sub 0 plus b sub 1 cosine x plus b sub 2 sine x. Then what happens when I add them together? What is f plus g of x? Well, that become f of x plus g of x. That become a sub 0 plus b sub 0 plus a sub 1 plus b sub 1 cosine x plus a sub 2 plus b sub 2 sine x. Notice that that is in the same exact form as the function f or function g, but just with the coefficient different. And because just the coefficient being different, it would have to be within the span of S, because span of S consists of all linear combination of 1 cosine x and sine x, and this sum between f and g is a linear combination of 1 sine x and cosine x. That's why I have closure. And the interesting thing about it is the following. So all of these are basically trying to convert some of these function space that doesn't look like vector space, but try to get them to behave like a vector space. What do I mean by that? Well, I mean by this. If you look at f of x, would you go a sub 0 plus a1 cosine x plus a2 sine x? If I know I'm forming a span using 1 cosine x sine x, then this function, the only thing that actually important to me is just these three numbers, provided I know the span, what span I'm using. And then the function g of x is nothing more than this. Oops. And therefore, the sum of these two vectors which is this, is nothing more than just basically this vector. Okay, I ran out of room, so I'm going to just put it on the bottom. There you go. So essentially, even though in this particular subspace, we are dealing with a continuous function that basically formed by 1 cosine x and sine x, but if you think about mathematically, it's no different than me doing like vectors in R3, like 0, 0, 0, or a sub 0, a sub 1, a sub 2, b sub 0, b sub 1, b sub 2, or a sub 0 plus b sub 0, a sub 1 plus b sub 1, a sub 2 plus b sub 2. So that is the important part of forming subspaces or forming vector spaces using different objects, is to identify that once I choose the object that we use to form the vector space, then now all it become matter are just the scalar, the coefficient in front. And hopefully some of you actually make the connection, is that in here, remember, the span, the vector that we use to form the span, are become nothing more than just the basis. And then we now have just the coefficient in front, which are called coordinates. So therefore, allow us to say, oh, well, if in R3, we're doing the coordinate being x, y, z with some vector as the basis, or center basis, e1, e2, e3. But now, all of a sudden, we can now talk about continuous function subspace. And when I do that, I can define a continuous function subspaces with 1 cosine x sine x. And now, once I do that, the entire continuous function subspace just turn into R3. Because it no longer matters that I'm referring to 1 cosine x sine x. That's now become completely irrelevant for most of the calculation we're going to do, because all I need to know are the coefficient between those three things. And then now I can just simply work with the coefficient. And once I finish the coefficient, I can then say, oh, now I have to put back into a function. So now I can do that. So it's the same way as how coordinates being used. So if I represent something using a specific basis, once I establish what the basis is, I can now just work with the coordinates and do the exact same thing I'm doing like is a regular vector. And once I finish with the coordinates, I can then say, oh, now I can combine the coordinate with the basis to now find out what it is. So that's the most powerful part of why we talk about vector spaces and subspaces. And you'll find out that the important thing, spoiler alert, the important thing about differential equations is that their solution almost always forms some kind of subspaces within a larger vector space. So without establishing this concept first, it becomes harder for us to understand how to form the solution of a differential equation, how to interpret it. All right. Unfortunately, my time is up. It's is almost 30 minutes. So I guess we can definitely talk about these questions right here during class. Or some of you might figure out the answer. Can post your work on Google Classroom. Give you hints. It's nothing more than solving a system equation. Okay, so if you figure it out, and feel free to post in Google Classroom. I know some of you like to do that. Post your work in Google Classroom and show everyone. And then maybe we can have a discussion in Google Classroom. That way we don't have to spend time in class to talk about it, and we can move on. All right, I'll talk to you later. Okay, bye-bye.